Hi, this is part 2 of the lecture on determinants. So, the determinant of a square matrix is defined in terms of a sum that you can consider this sum as a linear combination. And so we're referring here to a matrix A, and we define the determinant of this square matrix A as a linear combination of the cofactors. And so one important thing to remember is that you can choose in this matrix. Here's a representation of this matrix A. You can choose a column, okay? You can choose a column, say column J, or you can choose a row on this matrix. Here is row I, is something that you select, and then you expand over that particular row or that particular column. Sometimes you make that selection, that row or that column, in a way that is convenient, because this operator is defined in a way in which it doesn't matter which row or which column you choose, the sum adds up to the same number. Okay, so either you choose one particular column when you consider this sum that involves cofactors, involves the entries over that column, for example, then you're going to have to carry out this multiplication, right? That entry times that cofactor, entry times cofactor, and so on. Add them up, and then that will be a number. We are here assuming that we're working with complex numbers, with entries. This vector space is the vector space of square matrices that have complex numbers as entries, and therefore this linear combination will also be a complex number. So the determinant of a matrix is here assumed to be a complex number. And so we can visit some examples in how to apply this definition. So here is one example. We have a 3 by 3 matrix, and one thing to point is that if we have any zeros, okay, if we have a column or a row that contains zeros, we would like to choose to expand over that particular row. So for example, here this is simply an illustration of this definition. As you can see, this cofactor here is the cofactor for row 1 column 1, row 1 column 2, row 1 column 3. So clearly what's happening is that we are expanding over the row 1, or the first row of the matrix, and you see the entry on position 1 1 multiplied to the cofactor, entry on position 1 2 multiplied by cofactor C sub 1 2, and then importantly that 0 is in position 1 3, that is multiplied by cofactor C1 3, which means that we don't really need to calculate that cofactor, because in any way will be absorbed by multiplying by a zero multiplication. So we only have to compute C11 and C12. And in this case, if you remember that cofactor involves the minor on entry by excluding row 1 and column 1, and that is what you obtain. That's where this determinant of that submatrix, the determinant of this submatrix, comes from. And then the next thing is to eliminate row 1 and column 2, and that gives rise to this other determinant. That's the so-called minor, right? So we have to keep track of these powers of -1, and this calculation reduces to be equal to -1. So the important thing is that we chose to expand over the first row. If we chose to expand over a column of this matrix, or over a different row, then we would verify that regardless of expanding over a different row or expanding over a column, we would find that the determinant of this matrix is always equal to the same value, which in this case is -1. Following up with this idea, we here can verify that the determinant of this matrix is still the same value, no matter no matter if we choose to expand or something else different than the first row. For example, if we expand over column 3, we would exploit the fact that there is an entry here equal to 0 on position 1, 3, and this sum, this linear combination with coefficients equal to the values in that column, appearing here 3 and minus 2, are appearing as coefficients of those cofactors C sub 2, 3 and C sub 3, 3, and this leads to the calculations involving, remember, for this cofactor, you're looking at the minor obtained by excluding row 2, column 3, and so that leaves you with values, these values, which are the values of this matrix here, of this sub-matrix, the 2 by 2 matrix. And then when you move on to 3, 3, you're looking at the sub-matrix obtained by excluding row 3 and column 3, and is this other 2 by 2 matrix. And so the calculations here will also lead to the value of minus 1, which we had previously computed, and this checks out. So to even make the point even farther, to emphasize that there are certain entries along sometimes a particular row, or entries that are entries of a column of the matrix, and we can exploit the definition of the determinant by trying to choose or select the row or column that has as many zeros as possible. So here is an example of a matrix that has, in fact, a row of zeros. And when this happens, when we have a row of zeros, then we can simply choose to expand over that row of zeros, and we will find that the determinant of the matrix will be a linear combination in which the coefficients of that linear combination, each coefficient is equal to 0, and this saves us a lot of work because look at here, all these cofactors C sub 6, 1, C sub 6, 2, all the way to the cofactor C sub 6, 9. We don't need to really compute those cofactors. They become 0. This is a sum of zeros which equals to 0. So when there is a matrix that has a row of zeros, the determinant equals 0, and similarly that would be the case if we have a matrix that has a column of zeros, as it is the case in this example. And for the same reasons, by applying the definition of the determinant of a matrix, we obtain the determinant of this matrix equals a sum of zeros, which in fact is equal to 0. So there are matrices that have certain structure. They're known as triangular matrices, and this means that the structure is such that there are certain entries of these matrices that are 0. In some cases, the zeros lie. You want to really picture. You want to picture the matrix as a square, and you want to picture the diagonal entries, which is exactly something that looks like the diagonal of a square. And so what happens is that either above or below the diagonal, there will be a lot of zeros. So this is the case in this example, in which the zeros are located on the upper part of this matrix. And so the entries that lie below the diagonal are not necessarily 0. Some of them may be 0, but for sure all the zeros are here located in the in this portion of the matrix. So this matrix is called triangular. In fact, it's called lower triangular, because the entries that are not necessarily 0 are below the main diagonal. So these matrices with such structure are going to be important because the calculation of their determinant is going to be straightforward. In fact, by choosing to expand by choosing to expand over, say, for example, the first row, we realize that a lot is similar to what we were discussing before. When you have a row of zeros, the calculation becomes rather very simple. Here's almost a row of zeros with the exception of the first entry, the 1 1 entry. And if we compute that cofactor, that's where this power of -1 comes from, and then that involves the minor of the submatrix that results by eliminating column 1 and eliminating row 1, and that leaves us with the determinant of this submatrix here, a matrix that has 4 rows and 4 columns. And then if we take a look, this matrix is still lower triangular, so we can choose to expand, to compute that determinant, expand over the first row, and that is going to lead us to the calculation of a determinant that results by excluding the first row and the first column of that 4x4 matrix, which means that now we're dealing with this determinant of this 3x3 matrix, and we keep track of the numbers that we were multiplying from the beginning. Okay, and so by calculating the determinant of this 3x3 in a way in which we expand the cofactors along the first row, now we're left with the determinant of this 2x2 lower triangular matrix. So what we obtain here in conclusion is that the determinant of this is a 5x5 lower triangular matrix, but when it's an n by n lower triangular matrix, this sequence of steps simply are consistent, and you would arrive at the analogous conclusion that the determinant becomes the product of the entries along the diagonal of this matrix. That is exactly what we obtain here. It's a multiplication of those entries. That's exactly what the determinant of a triangular matrix. And this, for the sake of illustration, we're using a lower triangular matrix. You can work out these calculations with an upper triangular matrix in which the zeros are below the diagonal and the entries that are not necessarily zero are in the upper part, and you will still find that the determinant of such matrix is still the multiplication or the product of the entries along the diagonal. So this is an example of a matrix that has zeros below the diagonal. This is what we would call an upper triangular matrix. We introduce some notation here where you can write the words DET for determinant, and or you can also use a notation that's similar to absolute value. That also stands for determinant of a matrix. So we're computing the determinant of this triangular matrix. This proceeds basically as we did before. We choose to expand over the first row, and expanding over the first row of each of these submatrices leads to basically end up with the multiplication of the entries along the diagonal here, right? And that 2 times -1 minus 3 times 3, 2 times -1 minus 2 times 3 times -1 times 5, and that's going to be equal to 30. And in a final note here, so we would like to point that when a matrix is non-singular, then the determinant of that matrix is going to be different from 0. So non-singularity, a matrix being non-singular, there's a lot of things that are equivalent statements here, but a non-zero determinant is going to now be related or linked to non-singularity.